Yeah, thank you. So a quick logistic announcement. Some of you have been asking about Tao Raven. So unfortunately, she has to leave. She has a family emergency to deal with. So for the remaining of the workshop, if you have any questions, comments, and requests, please continue to come see Shubhangi and me. So yeah, we're very sorry that she cannot be with us till the end of the workshop. So now, this afternoon, we're very, very pleased to have Jennifer Chayes here. So as you know, Jennifer is the Associate Provost and Dean of School of Information at Berkeley here. Now, before coming to Berkeley, Jennifer had a long and distinguished career at Microsoft Research. She was the founder and managing the director of 3 labs over there. So Microsoft Research in New England, in New York City, and in Montreal. So without further ado, so let's listen to Jennifer.
Okay, and I just want to say that I'm Associate Provost of the Division of Computing, Data Science, and Society, of which School of Information is a part. And just as I was pulling into the parking lot here, I got the notice that the proposal for us to become a college just got through the Berkeley Academic Senate, just as I was driving over here. So we're, yeah. So we're, hopefully less than a year away from becoming the first new college at Berkeley in over half a century. So, which is really exciting. And of course, it's computing, data science, and society. And so it relates to a lot of what many of you do. So who knows, maybe you'll be a part of the College of Computing, Data Science, and Society in the future. Okay, so a lot of this is going to be old material because I wanted to really explain what a graphon is. I'll make some allusions to new work. It gets much more complex. Yegane, who is here, knows how complex these things can get since she's been working with Christian Borgs the past couple of years. Okay, so first, I'm going to talk about the motivation for doing this. We started work on this. When I say that, it was Christian Borgs, Latsi Lovas, Vera Shoj, and Kari Vestergambi. So it was 3 women and 2 men who started this field. and that was around 2005 or so. So it's been a while. I'll talk about graph convergence and limits. So basically, how do you take a limit of a network? Then how, once you've thought about that, you get a very rich class of models of random graphs that can presumably be used to describe real-world networks. Then how do I take some measurements of an existing big network and from that predict the non-parametric representation of it as a 2-variable function? And then an application. So there are 3 related questions that we asked. We asked, what is the correct notion of a limit? If you make your notion really weak, then every graph will converge to a different limit. If you make your notion, and if you make your notion really strong, then everything converges to the same limit, okay? And, neither of those are very useful at extremes. So how did we come up with something that we thought was useful? And the way in which we did that was for dense graphs, a dense graph, the number of edges scales like the square of the number of vertices, so a positive fraction of the potential edges are occupied. And for dense graphs, we came up with about 6 different notions that all gave us the same limit. So we felt very good about that. We said, okay, we're on to something here. Then how do I non-parametrically model a real world network? By non-parametrically, it's a strange word to use in a way, because really what it means is that you have essentially almost a bigger space of parameters. So parametric is something like I have the graph GNP, it's described by 1 parameter P. As I do it, and I can go on and I can have like a stochastic block model where I have, K colors, K choose 2 parameters. When it gets to be so big that I can no longer describe it with a set of parameters and I need a function, then we say it's non-parametric. And how do I estimate a non-parametric representation for, let's say the Facebook graph or something, and then give it a very small, very sparse sample of a denser graph? How do I predict unobserved properties from that? Okay, so by analogy to thermodynamics as the limit of statistical physics, which was my training. I was a mathematical physicist by training, so I think of taking limits, or differential equations as the limit of interacting particle systems, in which I specify every possible interaction. And we all know differential equation is much easier to deal with. Is there a meaningful way to compare large networks by taking some kind of a limit? The second question, the modeling and machine learning, how can I take a single snapshot of Facebook or LinkedIn or something today and ask how the network will look when it's twice as large, or try to predict something about the network? This is a work that's a really old work, but it finally got published. We were kind of slow to write it up. So this is probably from about 2015 or so, or 2016. So you can get an estimate of the graph. So it's in the Annals of Statistics now. And then inferring missing entries. So if I have missing entries, I've got a certain number of people who've rated all possible movies on Netflix. How does Netflix get an estimate of whether you're going to like a given movie? Okay, so we start with graphs, set of vertices, and a set of edges. Edges represented by an adjacency matrix, which just tells us whether the pairs are connected or not, or a weighted adjacency matrix, so the density of the connection there. And from that, we get something which we're going to call graphons, which are going to be sigma finite measure spaces. I'll show you some examples, and a symmetric measurable function on those. Okay. So heuristically, if I take the adjacency matrix of a graph, so for example, if I take this graph, okay, and what I do is I represent it with an n by n grid, like a square, okay, and if there is a connection between a vertex 2 and 2 of the rows and 1 of the column, then I put an edge there, and then I will color it black in this representation. This could have been an n by n matrix with 1s and 0s. If there's a 1, I color it black. And then I say, okay, the limit is just like take the unit square and just look at that, okay? Or the random graph with p equals 1/2. I flip a coin and everybody has a half chance of connecting. And then I get something that looks like a constant density 1/2 there. But what about permutations of the vertices? So I could take this, and by relabeling, it would become this. Well, when I take this heuristic limit of 1, is it the same as the other? And the answer is yes. Okay, so this was done a long time ago with, whenever you see a B, it's Christian Borg's, and the L's I think are all Lovaas. They're mostly Laci Lovaas Sr. There's also a Laci Lovaas Jr. But anyway, this is with Lovaas Sr. That what you get out here, so the analog of an isomorphism of the analog of the permutation invariance of the vertices in a finite graph will turn into this function being unique only up to measure preserving bijections. Okay, so the limit of this and this are the same. They're in the same equivalence class. Okay. Here are a few more examples. If I take a uniform attachment graph and I order it by the vertex degrees, I get this function, which is a bounded function. If I take the limit of this, function on the unit square 0, 1, which I can think of as just a piece of the upper quadrant. And if I took preferential attachment and ordered it by degrees, I would get this, which is unbounded. So that's interesting. So preferential attachment leads to something unbounded. Okay, so the first thing we did, which if you're coming at it from an analysis point of view, you kind of always think this way. You think I want a metric to measure the difference between two graphs. And so we went back to some work by Fries and Conan. It wasn't done in this form, but it's basically from that. If I have two functions of two variables, okay, which I can think of as like representing two different graphs, how am I going to compare them? Well, what I'm going to do is I'm going to take the difference between them, but remember, relabelings shouldn't matter. Okay, so I take the difference between them, and then what I do is I look at the max cut, okay, the max cut of the difference through these. If I looked at just one, if W2 were 0, I would literally be taking the max cut through the graph represented by that W1, okay? And now because I have this permutation invariance on the graphs, it turns out that what I want to do is I want to take an infimum over all measure preserving bijections. Okay, so I would have, if I had finite graphs, done a min over all permutations. So I would have said the distance between 1 and 2, if they were the same size, graphs 1 and 2, is I take the difference between them and I min over all relabelings of the vertices. Okay, so here it's going to be over all measure preserving bijections, which is just kind of a continuum reflection of the permutation invariance. Okay, and then I say a sequence of graphs converges to a graphon in this metric if the empirical graphs, which the empirical graphons, you kind of saw that in the picture. If I take the graph and I represent it as an adjacency matrix, then with zeros and ones, okay, then I'm going to look at, so it converges to a W if in metric, if these empirical graphons converge to it, okay? So it's the pictures you were seeing, but always mod this measure preserving bijection. Just like when you think about graphs that are exchangeable, you say mod the permutations of the indices. Okay, so that's convergence in metric, and you like a metric because like you can bound things and and you're theorists, it's nice to be able to bound things. Okay, but there are many other notions that one could use, like subgraph convergence. So basically, I mean, don't think of the homomorphisms, just it's the same thing as saying, I am going to ask, so I have this sequence of growing graphs, and I am going to ask that the edge density converges. And I'm going to ask that the triangle density converges. And I'm going to ask that the 4-cycle density converges and the Peterson graph density converges. And I just, so along the sequence, I see what the edge density is, Peterson graph, all of these finite possible graphs. And if all of those converge, it turns out to be the same as metric convergence, which is not at all obvious, right? One is this very local thing, and this metric convergence has to do with cuts. And in fact, there were, as I said, about 6 different notions for dense graphs in which the number of edges scale like like n squared. So where, a positive fraction of the possible edges are in there. And so there's a statistical physics way of doing it. I can represent ground state energies, basically. There's looking at convergence of all the max cuts and min bisections. There's something to do with Samaretti partitions, if you've heard of those. There's also convergence of a large deviation function corresponding to having an ensemble in which the vertex weights are fixed and the edge weights are fixed, and all of these. So this is me and Christian Borges with Lovas and Shoge and Vestergambi, and then later with David Gamarnik for the large deviation stuff. And these are all the same for dense graphs. So dense graphs are really, really nice. And you've got a good notion because everything is giving you the same notion. Okay, how about graphs of bounded degree? These are much more fragile. There's a notion of convergence called Benjamini-Schram convergence, which has to do with if I take a rooted point and I look as the graph gets bigger, I look at the local neighborhood of that rooted point. That if that converges, that's Benjamini-Schram. It turns out that subgraph convergence and Benjamini-Schram convergence are the same thing on sparse graphs of bounded degree. Convergence of these free energies is a strictly stronger notion, and large deviation is stronger even than that. So not getting these nice equivalences among all the different kinds of limits. And then the sparse graphs of unbounded degree are probably the ones we care about the most, okay? When we look at things like Facebook and LinkedIn and just the nature of human interaction, okay? They're sparse. I'm not connected to a positive fraction of the people in this world, okay? As the world gets larger, it's not, my number of connections is not growing like n squared as the number of people in the world gets bigger. However, there's no bound. Like there are people who have an arbitrary number of connections. So it's sparse. If I divide by n squared, the probability of a connection is going to go to 0, but it's not going to be bounded. Okay. And so most real life networks that have to do with human beings are sparse. The existing graph things correspond to a trivial limit. So power law graphs and a lot of these things are sparse, unbounded. And so we want to develop a theory which works for that. And we came up with a different notion about 3 years ago called 4 years ago, sampling convergence, which I'm not going to talk about much here, but is yet another way of doing it that generalizes nicely from dense graphs to sparse graphs in a local sense. Okay, so let's just talk about sparse graphs with unbounded, so the average degree of the graph. Okay. The degree of the graph is diverging. So if I divide by n squared, it goes to 0, but think of it maybe going to 0 like log n over n squared or something. Okay, so think of it like the average degree might be log n or something. Okay, so log n diverges, right? If the probability, if I took GNP type graph and I said the probability of connection is log n over n squared, okay, or log n over n, okay. So what I'm going to do then is this is looking down on that 1-by-1 grid, okay, and what happens is that the L1 norm of this, if I divide through by the density of the graph, which is going to 0, this thing explodes. Okay, so I get these very high, right? So I'm dividing through by the density of the graph. This is getting large. And I say that GN is convergent if there's some function W of X and Y, now not a bounded function anymore. Okay, it's in R plus squared actually, such that this is going to 0. Okay, so this generalizes many of the results for dense graphs. I could do something entirely different to try to get a non-trivial limit out of it. Instead of dividing through by the density, okay, which took something that was going to 0 like the density and then made it not go to 0, okay, I could instead take the underlying metric and I could scale it by square root of the density. So in the first case, I'm staying on the unit square, but I'm getting unbounded functions. And in the second case, what I'm doing is I'm stretching the unit square to the positive quadrant. I'm stretching the underlying metric by square root of the density, okay? Sorry, square root of the norm of the graphons. And so I say that it converges in the stretch metric if I can find something that agrees with it in that case. So do these notions give, subsequential convergence or something like that? And the answer is no, because in this case, mass can disappear up to infinity. And in this case, it can disappear up. Okay, and here it can disappear out in the positive quadrant. And so solution, at the time we developed these theories for sequences obeying some notion of regularity, which ruled out the pathological ones where the mass was escaping up or escaping out. And we generalized many of the results for dense sequences, as long as the average degree diverged. Okay, so, think of it like log or something, log n or something. So the advantage of definition 1 is of the one where I divide through by the density is that it gives power law graphs converge, the degree distributions converge. We can estimate it from a single sample, so we'll be talking about that more later in this talk. And for bounded graphons, this can also be done in a differentially private way. So I'll talk a lot about all these things. The advantage of the second one is we get very long tails, which we might have in some real world graphs, okay? The vertices that appear early get larger degrees. So that also corresponds to the kind of thing that we see happening. It leads to a family of growing graphs. Okay, in the first case, when I renormalize, what I'm doing is I'm basically changing everything. A new vertex comes in, and then I have a new number of vertices, and I have a new WG. And so every time I change something, this other way can be viewed as I'm adding things on. So you're not. Yes, you can get more connections as time goes on, but I'm not changing the normalization at each time step. And also, and this is work that we've been doing more recently, even without this tail regularity, there's something called graph X's, which generalize graphons and may be appropriate in certain cases. And you can get a projective family of those. Okay, so can we get a sequence which converges in both senses, getting the best of both definitions, the best of both dividing through by the density or stretching the underlying metric by the square root of the density? And theorem says that if both these things happen, then it's dense. Okay, then we're just back to the old dense graph case. What sparsity can we achieve? You have to have divergent average degree to get either of these limits. So think of something growing like log n or, log star n. I mean, it doesn't have to be growing fast. It just has to be diverging with n. The average degree has to be diverging. Okay, so now what we've seen is that we can take graphs and we can get these functions W, which basically describe the edge density in various ways. Now I want to think about, and they turn out to be non-parametric representations of our underlying graph. Now I can start with a feature space and connections that come in a symmetric measurable function telling me the likelihood that these latent features may be connected to each other. And from that, generate graphs which are consistent with this. So we all know, or I hope many of us know, the random graph GNP. Okay, I say that any two vertices are connected to each other with probability P. I flip a P-weighted coin. P might scale like 1 over n, or it might be a constant, whatever. Okay, so I can generate a whole class of random graphs with this model, right? When I get these W's, I can actually generate whole classes of much richer random graphs. GNP corresponds to constant W. W of X and Y equals a constant. It could be a half, it could be 1 over n, but it doesn't depend on X and Y. So I can get something much richer class of models from it. So generating dense random graphs first. The traditional model for dense graphs is what's called the stochastic block model, which is a generalization of the random graph. The random graph has one color of particle. They're all the same color. And I connect them to each other with probability P. I connect any 2 points. Let's say I had red and blue colored points, colored vertices. I could have one probability for connecting red to red, one probability for connecting blue to blue, and one probability for connecting red to blue. And since this is not directed, Yegane worked on some directed things. Since this is not directed, P blue red equals P red blue, okay? So if I have K colors, I have K choose 2 parameters, and very often, going back to 1983, which, my God, that's a long time ago. It's almost 40 years ago. People would use these as kind of a generalization of the random graph. Okay. And they try to fit them to things. The newer non-parametric models are still, it goes back 20 years. But I want to think of it as I'm given a feature space and a distribution over that feature space and a graph on. So I'm going to choose points in this feature space according to the distribution pi. So I'm representing it as one-dimensional, but it's not one-dimensional. Let's think, what are the possible features that might be relevant for you connecting to me on Facebook? Okay. It could be my age. It could be my height. It could be the field of my degree. It could be my income. It could be my preferences in music, my preferences in food, my preferences in politics, right? There's like a huge space of possible latent features that might explain why I connect to you. I don't know what all those features are. I just see, oh, there are these connections, right? So I'm going to now start generating us. So I've written it as one-dimensional. It's not one-dimensional. I could give you 100. I could give you 1,000 reasons why we might be connecting. So, X1 is born or enters Facebook with a certain set of these latent variables that are characterizing who they are. Okay. X2 23, I've taken a 1,000-dimensional space and I've projected it down into one thing. So the third one that was born is the smallest in this projection of the 1,000-dimensional space onto a one-dimensional space. So all these guys are born, okay? And then what I'm going to do is I'm going to connect X17 to X4 with probability W of X17, X4, okay? And then later right. And so let's say somebody just gave you walk in, you're a new employee of LinkedIn. Somebody says to you, by the way, you've just joined. Here's the W function of LinkedIn where you just, right? So here it is. And now I can denote the resulting graph that I generate by flipping all these W of X and Y weighted coins where X and Y are my attributes and your attributes. And I'm going to say that's an inhomogeneous random graph represented by W, okay? The special case of W being a constant is GNP, okay? Or W being, piecewise constant with K choose 2 parameters. That's the block model, K colors. Okay. So Bolobash and Reardon did this for bounded W. So given a feature space and a probability distribution over it and a graph on, I'm going to do exactly what I said to you. I'm going to generate all these, and then I'm going to connect I and J with this probability where I've now properly scaled it by the density, just like I was doing that first way of normalizing something with unbounded average degree. So I don't connect you with just W of X and Y, because what if X and I is W of X and Y is unbounded? It's not in the case considered by Bolobash and Reardon, but what if it's unbounded? Okay. And the resulting random graph, they called an inhomogeneous random graph at target density rho n, and I denote it by that. So in other words, let's say, you just started at LinkedIn and they say, hey, here's our target density when we have n people on LinkedIn, and here's the W that describes LinkedIn. Now start generating realizations of them. Okay, so it generalizes sparse or Renyi graphs, power law distributions you can get easily, and it converges in this cut metric that we defined. If the average density goes to infinity, and the first moment of the density goes to infinity, and the density itself goes to 0, and this GN is exchangeable but not projective. Why is it not projective? Because I keep renormalizing at every stage by dividing through by the relevant WN. So I'm effectively removing edges. Okay, so I can't think of this as something actually building up over time. And now I'm going to do something different. Caron and Fox did this for a W of X and Y that was basically a function of X times a function of Y. Okay. And then Roy and Veitch did it in a more general case. So again, we have a sigma finite measure space and we have a graph on. And what I'm going to do, and still the points in omega represent you with all your underlying latent features. I don't necessarily know them. But that's what it could be based on. And now what I'm going to do is I'm going to have a Poisson process with intensity T mu, and I'm going to generate individuals with their entire set of all these latent features in this Poisson process. And then I'm going to connect I and J with probability W of X, Y, X, J. I gave you a W, you walked in the door, LinkedIn gave you their W, okay? And then I'm going to remove isolated vertices and get a finite graph. And the first time a vertex appears is its birth time, but so let me give you an example of this. So what I've done is this is at time T1. Again, I have a one-dimensional representation of this 1,000-dimensional latent feature space, okay? And so at time 1, somebody's born with this feature, which is, it's a set of 1,000 features, okay? And at time 2, this. So this is somehow a one-dimensional representation of this 1,000-dimensional space of your possible features. Okay, and then what I'm going to do is I'm going to flip coin, W of X and Y. We did coins, okay? So I'm going to say somebody with, somebody born in this country who's now this age, who's living in that country, who loved physics, who hated chemistry, whatever. Okay, the probability that they're going to connect to somebody else. And so what happens is that at time T1, these 4 vertices have been born. 2 got connected to 4. That flip came up heads. 2 got connected to 3. That flip came up heads. 3 and 4 did not connect. The flip that they did not connect. And 1 did not end up connecting with anybody. So they're not in the picture yet. Okay, now by time T2, 3 more points have appeared with their sets of features, okay? And so what has happened? So when X5 was born, it tried to connect with X1 through X4, nothing happened, okay? 6 got born. It did all of its coin flips. Wow, it connected to both 4 and 2, but not to 3, okay? And then X7 got born, and it connected to 1. Okay, nobody had connected to 1 before. 1 was on Facebook, but nobody had connected to it, okay? But now somebody's connected with it. So now 1 shows up by time T2, 1 shows up. Okay, and so these are, if we use that first definition where we are doing the renormalization by rho n, that's what happens. If we do the second one, we get these very long tails. Okay, now I'm going to tell you about a third one, which just sounds so weird. And these are graph X's, if you've heard of graph X's. They turn out to be the completion of sparse graphs under some very natural convergence called sampling convergence. So now what I'm going to do is I'm going to give you 3 things, okay? I'm going to give you a W of X and Y, which is going to tell me that if Shubhangi has feature set Y and I have feature set X, this is the probability that we're going to connect, okay? It's going to also tell me that there's a 1 variable function, an integrable one, which tells me, so, the star function of my set of features is a certain number. That's going to be indicating to me how many people kind of connected to me just because of my star power. And then Yegane has a set of features, okay? And she is going to have a certain star power, a certain number of people who connect into her, okay? And then there's this constant that represents dust, which are, and it's got this norm. And what I'm going to do is I'm going to create a Poisson process just like I did before, but I'm going to join Xi and Xj with probability W. I'm going to grow a star, and then I'm going to independently add isolated edges. And what this lands up looking like is this very interesting thing that is a little bit richer. It doesn't just say that we connect with each other. It also has kind of, it's not directed, but it's kind of elements of Twitter with the star power, and it has some other elements. And and I'm not going to tell you all the history of all this stuff, but it gets complicated. Okay, so now what we did, I'm not going to get through all of this, but that's okay. So what we did was we had a set of graphs. We showed how by various notions of convergence, they could converge and give you some function, which was, presumably like, well, what is that function? What does that have to do with the graph you started with? That's what we're going to be asking. If I give you that function, you can generate things that are consistent with it, just like if I gave you the constant function P, you could generate a random graph. a Erdős-Rényi random graph. And now I'm going to ask, given a snapshot, you've walked in, you start doing measurements on Facebook. Can you actually estimate their W? Okay, so from a single instance, can we predict a similar graph? Okay, the traditional approach for modestly sized graphs went back to 1983, and everything said, oh, I'm assuming everything I look at is an example of a stochastic block model. Okay, so so I'm going to try to approximate it by a stochastic block model. Now, what is the problem with that? If I have 1,000 features, okay, and I have all these different values for those features, some are a continuum of values, some are a set of discrete things. How many colors do I have? I have a really large number of colors. I mean, an infinite number of colors, right? Because I've got, like, even if they were all finite set, it would still be this astronomical number of all the configurations of these 1,000 features, okay? So these things don't scale properly. The best stochastic block, if I say to you, I want you to go in and measure all the possible parameters, which are growing, the number of parameters are growing exponentially factorially in 1,000, okay? That's not very good. It might be better to ask you to estimate a function. So do a non-parametric thing. Give you a function rather than give me the 1,000 factorial parameters. And how badly would misspecifications give you the wrong thing from those 1,000 factorial parameters, okay? So the non-parametric approach is model it as a W, estimate an approximation to that W, and then I can generate a new graph using that W. And so our task is to estimate the approximation to W from a single sample, okay? And so the thing which I said was done in about 2015 or 16, but we finally had it published in Annals of Statistics. If W is an L2, so if it's square integrable, if the density is going to 0 and the average degree is diverging, no matter how slowly, log star is fine, for example, then we can consistently estimate this. And I'm not going to tell you how we consistently estimated it. It is, there's almost like a max min type procedure that's going on. Okay. Okay. Now I'm going to look at, oops. Now I'm going to look at, can I do this differentially privately? Even for things like databases, we really worry about what gets revealed with me in a database, okay? And so differential privacy says, if I'm in the database or out of the database, I can do a measurement that's epsilon differentially private if my being in the database or not being in the database only changes things by epsilon. For graphs, it's much, much worse than this, okay? Because a lot is revealed about me simply by virtue of who I'm connected to. Okay, so there were, studies that go back now many, many years saying, oh, I can, with high probability estimate if you're LGBTQ based on your connections. I can estimate your religion based on I can estimate all kinds of things. Your friends tell you something about me, okay? Or something about you. So, a randomized algorithm is epsilon node private if for all graphs that differ in at most one node, the measurement I take the algorithm on that graph won't change by more than plus or minus epsilon, basically. Okay, so that's saying if you're in the graph, if you're out of the graph, an algorithm on that graph, the randomized algorithm itself is node private if applying it to the graph won't change the result by more than epsilon. There's an analogous definition for edge privacy, which a lot of people have worked on. It's easier, but it's not very useful. If the edges in there are not in there, how much do things change? Okay. I'm not an edge, I'm a node. Okay. And so I don't care if you put the edge or don't put the edge. Okay. So if I'm connected to Bill Gates or I'm not connected to Bill Gates, fine. You know, but I really want to know me as a node with all my connections. What does it say if I'm in or out, right? And so previous work had been looking at edge privacy in dense graphs, and our task was node private estimation of general sparse graphons. And so what we showed is that for a bounded W, where the density was going to 0, and the average degree was growing at least as fast as log n, we could actually show that I could estimate what the graphon was in a way that did not reveal that, only changed up to one, order 1 plus or minus epsilon. So the estimation of W is not revealing very much about you if W is a bounded function. And then later, so this was with Christian Borgs and Adam Smith, who's one of the inventors of differential privacy, and then with Ilyas Zadik, 2018, we showed more than that. So the algorithm that gets used here, so what gets used is that you consider a whole class of possible random graphs. I could consider something as simple as just Erdős-Rényi random graph. Okay, that's characterized by one parameter P. I'm trying to estimate what the random graph is. So that's just a question of how well can I estimate P? Well, what algorithm would you do? I would just, sample randomly and see whether it's there or not. So I take, right. So I take a large sample of pairs of nodes and see if an edge is there. So that's the algorithm that I'm using. That turns out to be a good algorithm. So these, the bounds that you use for differential privacy are min-max in the following sense. What I do is for any given algorithm, so one could be just this counting algorithm, or so I fix a set of models. So my set of models could be just the random graph. It could be all stochastic block models. It could be, could be bigger and bigger classes of models. For that, I look at the behavior on the worst possible graph, the one that's going to mislead me the most. Okay. So that's my max, but then I min over all classes of models. Okay. And for the fixed algorithm, I min over all classes of models, and that's how you get the bound. And so if I'm doing an estimation of W without requiring differential privacy, I land up getting certain bounds on how well I do or don't do. In the work just with Adam Smith, we had showed that we could do a differentially private estimation, but our bounds on that in epsilon, we were not, as we took epsilon to 0, as we required no privacy, the statistical estimation did not do as well as if we had privacy in there. And here we came up with a different way of doing it with Ilyas, where you got the same min-max lower bounds and upper, that they went to the same function. as epsilon was going to 0. So because we were asking, what is the price of requiring privacy in our estimation? Okay, and now I'll do a really fast application for you. So I'm trying to estimate from your rankings on Netflix or Hulu or whatever, what an entry is going to be. I want to tell you what the likelihood is that you're going to like this film, and so Netflix says to me, oh, you have a 96% agreement with this, or you have a 70% agreement or whatever. They're telling me how likely I am, or social network completion or weighted social network completion. So what these are is these are matrix completion problems. Okay. I've got films, I've got users, and I want to estimate a missing entry there. Okay. What I have is from all the ratings, I'm Netflix, what I have from all the ratings is a very sparse sample of all possible things, right? So what the Aldous-Hoover theorem tells me is that our exchangeable organic matrix can be written, this unknown thing can be written as a function of the features of the rows, like all the features about me as a person, all the possible, and the columns, all the possible features of a movie. I don't know them all, they're latent features, right? And some IID variable chosen uniformly at random. So here we are with that. And then what I'm going to do is I'm going to observe each entry independently with probability P, and that's going to get rid of this epsilon. And D is going to denote the maximum dimension of the latent spaces. So there's like some dimension of the latent spaces of characteristics of people. There's some dimension of the latent space of movies, okay? And I'll just take the max of those two. Given an observed matrix, can I learn the expectation of this to be able to recommend a movie to you? And ideally, you'd like to estimate, constant degree. You don't want to have to have people rate any more than a constant number of movies as n is growing. Okay, and Chatterjee had done this, that P would have had to sample a lot more than that, okay? So you would have had to sample, some much larger fraction of the movies. And so the challenge of sparsity is that there's no overlap. There's me and there's Yegane, and I've rated Panda movie and something else, and she's rated Nemo and something else, and there's no overlap. So if I try to expand my neighborhood and say, okay, well, that movie, there are 2 people there who have rated it, and those people have rated some other movies, and finally I get some overlap. And how far out do I have to go? Well, this, by the birthday paradox, has to be large enough. And then it turns out that if I sample with this density, I'm going to have some overlap. Okay, and what I'm going to do is I'm going to compare my product ratings along these paths. And the result of all that is that with a probability that does go like 1 over n, okay? So I just have to sample of order d squared n. Okay, d squared is still pretty big, but at least, I could put a constant in front of that and it would still be a constant, okay? And so this is much better than the previous one. So we learned about graph convergence as a way of comparing graphs, okay? Dense graphs, bounded degree graphs, and even sparse unbounded degree graphs where we either had to normalize through by the density or we had to stretch the underlying space. Graph funds provide a way to generate much richer random graphs than Erdős-Rényi or stochastic block. You can use the inhomogeneous random graph. You can use this graph-on process or even a graph-vex process. And I can consistently estimate these graphs. So I can consistently find the W that represents some graph, okay? And I can even do it differentially privately if W is bounded. And then, there are many up, and there's going to be a semester at Simons in the fall, which is going to involve graphons and networks. And, in the subsequent years since we started developing this, it's just been applied in hundreds of different circumstances. So maybe now when you hear graphon, you'll have a little bit of an idea of what it is. Thank you.
So basically, when you have like a set of observations of graphs or just a huge graph and you want to build W, you're gonna approximate W basically, right?
Yes.
So in huge graph, there's probably a way to sample the graph to evaluate W in a better way, right? So what would be the strategy to do that?
Well, okay. So the proofs, which are very, very, very general, it takes way too long. Okay. You're basically approximating it by stochastic block models of various sizes, permuting over things. So the proofs, which cover all the worst case scenarios, okay, are not very efficient. But you can say, I'm going to look over a class like a stochastic block model and then take the limit of that. Okay, that is one way of doing it, but you need some hacks. Otherwise, it will take forever. Okay, so to provably
if you have some prior information about the distribution of the graph, is it better to use this distribution to sample the graph to evaluate W better?
Yeah.
Thank you for the talk. I'm just wondering what are some like one or two open questions in this area which are like.
So, even in the theoretical area, there's a lot actually. So we did all the estimation stuff for the inhomogeneous random graphs, but the ones that are the process, which are people in the statistics community are very excited about, we haven't done any of the estimation theorems for that. So it's a really, I think it's a really important question to prove that you can estimate things properly using this other way of doing it with that comes about from this graphon process. Okay, so
that would
we have come up recently with something which we call sampling convergence, where we were able to show that we can do some things where sampling convergence over time you have a Poisson process that tells you how to sample. Okay, so but do the estimation theorems based on that, for example.
If you have an estimation of W, could you use W to generate like a generative model?
Oh, yeah. Okay. That's the whole point of it. If you can estimate W, then then you can have oh, I want to learn something about this network. I can generate things which are distributionally similar to the graph I've gotten. I can try all kinds of things on them.
So you could build like a synthetic data set from sampling Facebook and generating new graph that doesn't really exist, but they mimic the distribution.
Yes, absolutely. I mean, that's one of the big points of this. Why do you want this W? So that you can generate things which are distributionally the same.
Yes. There are works that people did on using this method to generate this data set. Is it like common? Or?
Yes, I mean, in the last 10 years, it's so we first started proving theorems about it. And I thought, was motivated by trying to do things on web spam. And I thought, what's the limit? And I asked Lovas, what's your notion of limit? And they didn't have any. And it's like, oh my God, somebody has to develop this. We went off into what I called math land. And then I don't know when it was, maybe 2012, I went to NeurIPS, and there were all these people doing graphon estimation, without proofs proving that any of it could work. But yeah, people just grabbed onto it because, of course, you don't want to do a parametric estimation where the number of parameters you need is growing factorially in the potential size of the latent space, right? I mean, that's a nightmare, right? Better to get a function and assume some properties, some smoothness properties or something about it.
So I have a quick question. So essentially you were creating a recommendation system, right, for movies and stuff. So before you guys created graphing stuff, what was the main algorithm that people used for recommendation system? And in your implementation of your algorithm, do you see sort of difference in performance?
So it's interesting because Deborah Shah, who is working with us, and Christina Yu, who is now Christina Lee, who is now Christina Lee Yu, was doing had a company on recommendations. And so some of this stuff was performing very well. Okay. So, people tried to do more parametric kinds of things before, which made things not scale very well at all. Okay, so you saw D's coming in the wrong place, the dimension of the latent space coming in the wrong place.
Let's say there's an existing algorithm on the Facebook network specifically. Say something about whether drawing a similar network on Twitter, like that algorithm, whether it extends on that, is there work on the kind of worst case to average case?
Well, so some of these theorems are exactly looking at, I mean, we can't prove the theorem without looking at worst case, okay? I mean, that's how we establish that something is possible, is basically we have to consider worst case. But I think robustness results would be really nice, okay, and not the average hardness results would be good.
So more questions we're going to take offline. So we take a short break and resume 3:30 our session.
We'll be back at 3:30 and hope to see everyone there. And I'll write the names of whoever's in the first session for this. Thank you very much.